In this video, we will learn a simple way to figure out whether the molecule is aromatic, non-aromatic, or anti-aromatic. We will do it step by step. I will show you the tricks that professors like to use, and we will also do examples as always because that's what makes learning very good. So, in order for the molecule to be aromatic, there are a set of conditions that it has to fulfill. The first one is it has to be a ring. If it's not a ring, it's not going to be aromatic. The second condition is that your ring must be planar. Most of the time, the molecule given to you will be planar. In unusual cases, it will be not planar if it has a lot of carbons. But generally, professors do not trick their students in terms of the molecule being planar or not planar. Usually, your professor could trick you, but usually that's not where the tricks come from. The third case, which is a little bit more complicated, is that the molecule must be conjugated. And conjugated means that every atom on the molecule on the ring has to have a p orbitals, and all the p orbitals will overlap to create a conjugated system. How do you know if the atom has a p orbital or not? So here I basically gave you most of the cases that you will see when you do examples, and this will allow you to determine whether you have a conjugated molecule or not. The first case is a carbon with a positive charge. If you see a carbon with a positive charge, it has an empty p orbital. This works. I put a check mark on it. Carbon with a negative charge works. Oxygen with two lone pairs works. Carbon with a double bond definitely works. Nitrogen with a lone pair works. Sulfur works. A nitrogen or other elements with a double bond would also work. So this list is not exclusive, but it basically gives you the most common cases. When would you not have an atom that has a p orbital? So if you have, most often it's a carbon that's connected to four bonds. If you have a carbon that's connected to four bonds, then that carbon will not have a p orbital, and therefore it will not make your molecule conjugated. So for example, if I have a molecule that looks like this, if you look at every carbon, why don't we go ahead and add hydrogen so we can see it more clearly. Remember, every carbon wants to have four bonds. This carbon has 1, 2, 3, so it has one hydrogen. This carbon has one hydrogen. This carbon has two hydrogens. So if you look, it is a ring, it's planar, but if you look at every atom on our ring, this atom has a double bond, like here, so that works. And this carbon has a double bond, so that works. But this carbon is attached to four bonds. It does not have a p orbital, so here it does not work. So this molecule would not be conjugated. And we will practice a little bit more, but that's the most common case when it is a carbon that's connected to four bonds that makes the molecule not conjugated. The last condition that is needed for a molecule to be aromatic is called Huckel's rule. Huckel's rule tells us that we have to have 4n plus 2 pi electrons in our ring, where n is an integer. It could be 0, 1, 2, 3, etc. So what we can do is we can right away plug in all of the possible n numbers to see how many possible pi electrons do we have. So here, if n is equal to 0, 4 times 0 is 0, plus 2, 2. So we can have, your molecule can have 2 pi electrons. When n is 1, it can have 6, n is 2 is 10, n is 3, 14. So in the fourth condition, you will look at the molecule and you will calculate how many pi electrons does it have, and I will show you how to do so. If it's 2, 6, 10, or 14, that works. So your molecule will be aromatic. Now, I just went up to n equals 3 because usually you don't get more than 14 electrons, to be honest. But of course, you can continue, you can go to n equals 4 and you will have a lot more electrons. But generally, that's all you need. How do you count how many pi electrons you have? So here again, I gave you a little guidance. If you have a double bond between two atoms in the ring, it's going to be 2 electrons. If you have a carbon with a positive charge, that means it's missing electrons, you will have 0. If you have a carbon with a negative charge, that's going to be 2 electrons. And if you have oxygen with 2 lone pairs, you only count one of them. The reason is I have drawn here. Let's say I have oxygen inside the ring. It will have 2 p orbitals. One p orbital will participate in the overlap and conjugation of the others, and one will be orthogonal to it. So we can't count both of them because one of these lone pairs will not overlap with the other p orbitals. It will be in a different p orbital in different space. So if you have oxygen with 2 lone pairs, only count one of them. This is some of the tricks that your professors will give you. How would you know how to count? Double bond is the most common one, but they can give you a carbon with a negative charge, oxygen. Same thing goes for sulfur. If sulfur has 2 lone pairs, you will only count one of them as 2 electrons. And then if you have nitrogen, for example, with a double bond and a lone pair, again, you will only count the double bond as 2 electrons. So I basically have talked to you about some of the tricks of conjugation. We went over different examples of whether a p orbital would exist in an atom or not, and same thing with the Haeckel rule. Now I just want to specify that if all of these conditions that we talked about are fulfilled, your molecule will be aromatic. If Haeckel's rule, if the molecule does not follow Haeckel rule, if it has 4n electrons, it's going to be anti-aromatic. And if the molecule does not follow any of these rules, usually, honestly, it's conjugation if your molecule is not conjugated. But if your molecule is not a ring, not planar, or not conjugated, so if it doesn't follow 1, 2, or 3, then your molecule will be non-aromatic. Not all schools ask about non and anti-aromatic. Some schools just ask whether your molecule is aromatic or not. But if you have to know whether it's non-aromatic and anti-aromatic, it will be non-aromatic if it's either not a ring, not planar, or not conjugated. And it will be anti-aromatic if it does not follow Haeckel, if it does not follow Haeckel's rule and it has 4n electrons instead of 4n plus 2 pi electrons. So with that in mind, let's go ahead and do our examples. Let's say this is A, B, and C. The first example, let's go through each condition. The first one was, is it a ring? Yes, this is a ring. Is it planar? Yes, you can assume it's planar. I told you most of the time they will not trick you with planar, with molecule being planar or not, but beware, it could happen. But if the molecule is small, it's most likely going to be planar unless it gets like 8 carbons or more, then you have to consider whether it is or it is not. Okay, so this molecule is a ring, it's planar. Is it conjugated? So let's look. This carbon has a double bond next to it, so this carbon works. This carbon double bond works, and this carbon has a minus charge that also works. If you look at on top where I said by conjugation double bond works, negative charge works. So this molecule is conjugated. So let's go ahead and list that. We can say it's a ring, or it's cyclic, it's planar, and it's conjugated. So the last thing we have to do is we have to calculate pi electrons. Right here, I already wrote it. We have a double bond, so that's 2. And then if you have a lone pair on a carbon, that's also 2. So we have here 4 pi electrons. Is it one of these? No, it is not. So it does not follow Haeckel's rule, because to follow Haeckel's rule, we must have either 2 pi electrons, 6 pi electrons, 10 pi electrons, or 14 pi electrons. And we can continue with that, but usually I said we don't get more than 14. So since it does not follow Huckel's rule, instead it follows the 4N rule. Because it's not following Huckel's rule, it will be anti-aromatic. And let's continue. Let's go to B. Is this a ring? Yes. Is it planar? Yes. Is it conjugated? So usually the problems are either with conjugated or with the Huckel's rule. Those are the two that are most of the time it will have tricks with. So let's see. This carbon works because it has a double bond. This carbon works because it has a double bond. This carbon works because it has a double bond. And so is this one. Now this carbon on top, if you notice, it's connected to two other carbons and it must have two hydrogens to have 4 bonds like it wants to. So this carbon has 4 bonds. And we said if a carbon has 4 bonds, it does not have a p orbital, and if it does not have a p orbital, this molecule is not conjugated. And since it's not conjugated, it will be non-aromatic. There you go. First trick was with the Huckel's rule. Now we see how they could trick us with the molecule not being conjugated. And now let's go ahead and go to part C. We see this molecule, it's definitely a ring. It's planar. Now, is it conjugated? Anything with a double bond works. So this atom works, this atom works, this carbon works, this carbon works, this carbon works. And nitrogen, we said that when it has a double bond, actually I did not put here nitrogen with a double bond, but I showed any element, if it will have a double bond, it will work as well. So, in this case, okay, it could be this way, and I think it's going to be positively charged here, or it can be like I have drawn here. So, all of these cases work. Basically, this nitrogen works because it has a double bond, so that works also. So it is indeed conjugated. And then finally, we have to count our pi electrons for the Huckel's rule. Every double bond is 2. We have 3 double bonds, so it's 6 pi electrons. And we said that when we have a nitrogen that has a lone pair and a double bond, we will only count 2 electrons from the double bond. So there's 6 pi electrons here. And so we go to the Huckel rule and we see, is it one of these guys? And we see, yes, 6 is here. So 6 pi electrons works. So this molecule is aromatic. This is Maya Alochi from Transformation Tutoring. I hope you enjoyed my video, and I look forward to seeing you in more of my general chemistry and organic chemistry videos.